Okay, so we'll go back to another video. So here we have a sum that we want to calculate. We have 1 plus 1 over 3 minus 1 over 5 minus 1 over 7 plus 1 over 9 plus 1 over 11 minus 1 over 13 minus 1 over 15 plus so on and so forth. Now you might be asking yourself, didn't you already do a video on this before? Because the digits, rather the sequence of what we're dealing with is very strikingly familiar from what I did in the past. Well, if you look at the numbers carefully, this is actually, and what I'll be describing is what is Leibniz's formula for pi. However, be careful because notice that the signs are different. Because Leibniz's formula for pi are the exact same sequences, but it starts off with a positive, negative, so the signs alternate, so on and so forth. Meanwhile, we have a plus, plus, minus, minus, plus, plus, minus, minus. So after every even term, we have that the sign switches. So this is a good rule of thumb to pay attention to the signs carefully before you jump to conclusions. So we know that, let's just, let me actually put this out into perspective first, that Leibniz's formula for pi says that it's the infinite sum from n is equal to 0 of -1 to the power n divided by 2n plus 1. So as described is exactly these numbers, but except the signs alternate from plus to minus, and it actually converges to pi divided by 4, which of course Leibniz's formula for pi. So just putting it out there. If you want to check that video, the link is in the description below and attached to the cards. And so going on to this sum over here, so we can actually write that as a nice infinite sum. So this is actually nice to say that this is written as -1 to the power, the floor of n divided by 2, and n divided by 2n plus 1. So now that question is, what does this infinite sum, or given specifically, converges to? So we don't actually need to do any sort of fancy rewriting, especially utilizing with the definition of the floor function, because what we can do is we're actually going back into more the terms of calculus, specifically with integration. Because what's nice is that by using integrals, we can actually go, in reverse to do the integration term-wise. And then from there, it's actually pretty simple that we'll actually utilize a little bit of some, some properties, specifically the geometric series that's going to come into play. So other than that, that's nothing really to get, it's really nothing to be afraid of here, to be honest. So this one's a little bit shorter than the other infinite sum. So with that, let's actually just jump right in. So notice that our given, I can write that as the definite integral from 0 to 1. So I'll integrate things in term-wise. So in other words, this is the same thing as written as 1 plus x squared, then minus x to the power 4 minus x to the power 6 plus x to the power 8 plus x to the power 10, and then let me actually just write two more terms, x to the power 12, then minus x to the 14, then plus so on and so forth, and then dx, okay? And you'll notice that if I were to use linearity and integrate both, from everything of our terms, it will actually come out exactly as this. Okay, so then of course that's the question, what is that equal to? So what we can do is let's actually do a little bit of some rearranging. So what I'll do is I'll separate this. So this, of course, is still our integral from 0 to 1. And I'll actually put in our parentheses such that we're separating things. So the first thing we'll have is we'll have 1 subtract x to the power 4, then plus x to the power 8, then subtract x to the power 12, and then so on and so forth. So the difference between with each degree is by 4. And so the next one, I'll separate that out. So we'll have now x squared, then minus x to the power 6, and then plus x to the power 10, minus x to the power 14, then plus so on and so forth, close that off, and then dx. So here's the interesting thing with our first, with our first infinite expansion of this degree over here. You'll notice that, of course, that not only that our x ranges in between from 0 to 1, we can actually notice that with this progression, we can actually write this as a nice geometric sum. What that is converges to specifically is that, or first let me write the sum, is that this is written as -x to the power 4 and then to the power n. And that says that that's the same thing is equal to 1 divided by 1 minus x to the power 4, so 1 plus x to the power 4. And it's still between the range from the absolute value of x is strictly less than 1, which is nice because we're dealing with from 0 to 1. So that's great. And then interesting thing here is that now what I'll do is I'll separate this out. I'll factor out the x squared. So I have x squared and then multiply with 1, and then minus x to the power 4, then plus x to the power 8, then minus x to the power 12, then plus so on and so forth. And you'll notice that this is actually just the same thing, but now all we gotta do is just distribute the x squared into here. So rather, in other words, this is the same thing written as x squared and then divided by 1 plus x to the power 4. And of course, it's still within that range. Okay, so with this now, let's actually combine everything back in together into one integral. Okay, so now putting things back together, so that means right here we'll have that we have the integral from 0 to 1 of now 1 at this with x squared and then divided by 1 plus x to the power 4th. So it doesn't look like it's easily, we can easily evaluate this like in an elementary perspective. I'll actually now divide everything by x squared. So now we have 0 to 1 of 1 plus x divided by, or 1 plus 1 divided by x squared. And then under the denominator, I have this as x squared plus 1 divided by x squared. So interesting thing from the denominator, I can actually factor this out or into a nice binomial. Well, in the sense that we're dealing this would complete the square, but although it's not exactly in that quadratic fashion since we have an x squared and an x squared over here, but we write things a little bit easier. So now I have that, so 1 plus 1 divided by x squared, and then under the bottom we have is x subtract 1 over x squared, and then add this with 2 and then dx. Okay, and now this is actually pretty easy from here. We'll just do a little u sub, so we'll let u equals 1 divide, or we'll let u equals x minus 1 over x, and so du is going to equal to 1, and then add this with 1 divided by x squared and then dx. Now we just plug all this back in together, so compute our new bound, so we let 1 equals x, so that means that's just going to be 0, then plug in 0, so that means 0 minus 1 over 0, that's like actually going to approach negative infinity, and so the du substitution, that'll get rid of itself, and then I have 1 divided by, so put this back in, so I have u squared, and add this with 2 du. Okay, and then this is straightforward that this is actually in a nice integration with arctangent. So using that special formula for, you know, the integral of the arctangent function, or rather in this specific case over here, it's going to equal to the arctangent. Said that wrong. So we have that this is 1 divided by the square root 2 multiplied with arctan of u divided by the square root of 2. Evaluate this from our bounds from negative infinity to 0. And then if I just plug 0, that's just going to be 0. So we first write 1 divided by square root 2, and then I have 0, and then minus, plug in negative infinity, that's actually going to approach minus pi divided by 2. And then if we just substitute everything out, this is indeed the final answer that our infinite sum, which looks like Leibniz's formula for pi, which is not, is going to converge specifically to pi divided by 2 times the square root of 2. And that is indeed our final answer to this strikingly similar sum that you're probably going to jump to conclusions thinking that, oh, I know what that formula is, but make sure. Good rule of thumb, as I mentioned, pay attention to your signs. It's always, you know, very helpful so you don't run into things like first on. So yeah, that's pretty cool if you ask me.